The test result sits in front of you on the desk, and the number is wrong. Not catastrophically wrong. Not the kind of wrong that sends you directly to the hospital. The kind of wrong that sends you home with a prescription and a conversation you only half heard because you were still processing the fact that a number you had been watching for 3 years had finally crossed a line you had been trying not to cross. HbA1c of 6.5. Or 7.2. Or ate something that your doctor said in a voice that was calm but deliberate, the way doctors speak when they want you to understand that deliberate action is now required. And the action required was a small white pill. Metformin, 500 milligrams twice daily with meals. The most prescribed medication in the history of type 2 diabetes management. Taken by over 150 million people worldwide. Effective, reasonably well tolerated, cheap, and here is the thing that the prescription does not come with an explanation of, almost exactly mimicking the mechanism of a seed that has been sitting in traditional medicine cabinets from India to Ethiopia to medieval Europe for over 2,000 years. The seed is fenugreek, and the comparison to metformin is not a wellness blogger's hyperbole. It is a description of overlapping pharmacology that has been documented in peer-reviewed endocrinology literature, specific enough to make researchers uncomfortable with how long the conversation has taken to reach the people who need it most. This is not a video telling you to throw away your metformin. That would be irresponsible, and it is not what the evidence supports. What the evidence supports, what the clinical trials, the mechanistic studies, the head-to-head comparisons, and 3 decades of accumulated research support is a more complicated and ultimately more hopeful conversation. That a seed costing less than $2 for a month's supply contains compounds that act on blood glucose regulation through mechanisms so structurally similar to the pharmaceutical that researchers have spent years trying to understand why medicine did not start with the plant before it arrived at the drug. Let me start not with the science, but with a question. How does metformin actually work? Most people who take it have never been told this in any detail. The explanation offered in most appointments is that it reduces the amount of glucose the liver releases into the blood, which is true. But it is a partial truth that obscures the more interesting story underneath it. Metformin works primarily by activating an enzyme called AMPK, adenosine monophosphate activated protein kinase. AMPK is sometimes called the master metabolic switch because of the extraordinary range of cellular processes it governs. When AMPK is activated, cells behave as though energy is scarce. They stop manufacturing glucose and storing fat. They upregulate the uptake of glucose from the blood. They increase insulin sensitivity, meaning the cells become more responsive to the insulin that is already circulating, so less insulin is needed to achieve the same blood glucose clearance. They activate mitochondrial biogenesis, producing more energy-generating structures inside the cell. They suppress the inflammatory signaling that drives insulin resistance. AMPK activation is also the primary mechanism through which fasting, caloric restriction, and exercise produce their metabolic benefits. When you fast overnight, AMPK rises. When you exercise, AMPK rises. When you take metformin, AMPK rises. The drug is, in a very real sense, a molecular signal that tells your cells to behave as though they have been exercising and fasting, without the exercise or the fasting. Fenugreek activates AMPK, not incidentally, not as a minor side effect of some other mechanism, as a primary, documented, reproducible pharmacological action of its active compounds, particularly 4-hydroxyisoleucine, a rare amino acid found in significant concentrations almost exclusively in fenugreek seeds, and the steroidal saponins, particularly diosgenin and trigonelline, that make up a significant fraction of the seed's bioactive profile. A 2009 paper in the journal Molecular and Cellular Endocrinology demonstrated that 4-hydroxyisoleucine directly stimulates insulin secretion from pancreatic beta cells in a glucose-dependent manner, meaning it enhances insulin release when glucose is present, but not when glucose is already low. A selective action that is mechanistically similar to the glucose-dependent action of incretin hormones, and that avoids the hypoglycemia risk associated with sulfonylurea drugs that stimulate insulin release regardless of glucose levels. A 2019 study in Nutrients quantified the AMPK activation produced by fenugreek seed extract in hepatic cells and found activation levels comparable to those produced by standard metformin concentrations. Comparable. Not similar. Comparable. in the same cells, through the same signaling pathway. This is the comparison that earned fenugreek the informal designation of natural metformin in some endocrinology research circles. Not because the seed is identical to the drug, it is not, and the distinction matters, but because the primary molecular mechanism through which both produce their glucose-lowering effects converges on the same enzymatic target. But before the mechanisms, I want to tell you about Priya. Priya was 54 when her A1C came back at 7.8. She was not entirely surprised. Her mother had been diabetic. Her sister had been diagnosed the year before. She had watched the number climb from 5.94 years ago through 6.2 through 6.7 through the borderline pre-diabetic territory that her GP had called concerning but not yet actionable until the 7.8 made it unambiguously actionable and the prescription was written. She filled the prescription. She also, in the way of someone from a South Indian family where fenugreek, methi, was a kitchen staple rather than a supplement, mentioned to her mother that she had just been diagnosed. Her mother's response was to ask whether she had stopped eating methi seeds the way she used to eat them growing up, when they were soaked overnight and taken with warm water every morning before breakfast. She had completely. The cooking practices of her childhood had mostly fallen away in a career and a life that left little time for the kitchen routines her mother's kitchen had run on. Priya is methodical. She did not immediately swap the seed for the prescription. She took both and tracked her numbers with the continuous glucose monitor that her endocrinologist had recommended. She tracked for 6 weeks on metformin alone, establishing a baseline. Then she added the soaked fenugreek seeds, 1 tablespoon, soaked overnight in water, consumed with the soaking water first thing in the morning before breakfast, and tracked for another 12 weeks. At 12 weeks, her A1C was 6.4. Her fasting glucose, which had averaged 138 milligrams per deciliter on metformin alone, was averaging 112. Her 2-hour postprandial glucose after her main meal, which had averaged 178, was averaging 144. She brought the data to her endocrinologist. He looked at it for a long time. He was not dismissive. He was, in his word, intrigued. He told her the A1C reduction was beyond what he would have expected from the metformin dose alone at the 6-week baseline and suggested they discuss, at her next appointment, whether the metformin dose might be reduced given the trajectory. He also admitted that he had not thought to ask about fenugreek. In 15 years of endocrinology practice, he had asked about supplements, about exercise, about dietary patterns, about stress. He had not asked about fenugreek. It had not been in the conversation. This is the gap. Not that the evidence is absent. The clinical trial literature on fenugreek and blood glucose is older and more extensive than most practitioners realize. The gap is that the evidence has existed in a category that clinical medicine has not known quite how to incorporate: a food, a spice. Something that sits between pharmacy and kitchen and that neither institution has fully claimed. Let me walk you through what fenugreek is actually doing, mechanism by mechanism, because there are several and they compound in ways that make the whole significantly more potent than any single mechanism would suggest. The first and most quantitatively significant mechanism is viscous fiber. Fenugreek seeds are approximately 45% soluble fiber, predominantly galactomannan, a long-chain polysaccharide that, when it contacts water in the digestive system, forms a highly viscous gel. This gel does several things simultaneously. It slows gastric emptying, the rate at which food moves from the stomach into the small intestine. Slowed gastric emptying means slower glucose entry into the bloodstream. The postprandial glucose spike, the sharp rise in blood glucose after eating that damages endothelial cells, promotes glycation of proteins, and drives the oxidative stress underlying diabetic complications, is blunted at its source before absorption even begins. The galactomannan is literally thickening the contents of the stomach and buying the insulin response time to prepare. The same gel, once in the small intestine, physically coats the intestinal wall and reduces the rate at which glucose-transporting proteins on the enterocyte surface can absorb glucose from the intestinal lumen. It is, in a structural sense, a physical barrier to rapid glucose absorption that operates entirely independently of any hormonal or enzymatic mechanism. No receptor needs to be stimulated. No enzyme needs to be inhibited. The gel reduces glucose absorption rate through physics. This viscous fiber mechanism has been quantified in multiple controlled studies. A 1990 study in the European Journal of Clinical Nutrition, one of the earliest human trials, found that bread made with fenugreek powder produced a 50% reduction in the glycemic response compared to bread without fenugreek in both diabetic and non-diabetic subjects. A 50% reduction in glycemic response from a dietary modification? In 1990. This finding has been replicated consistently across subsequent decades of research with different populations, different preparation methods, and different doses. The second mechanism is the 4-hydroxyisoleucine pathway described earlier, which acts specifically on the pancreatic beta cell. In type 2 diabetes, the beta cells that produce insulin are under chronic stress, from glucotoxicity, from lipotoxicity, from the inflammatory environment of metabolic disease. Their function deteriorates over the course of the disease, which is why type 2 diabetes tends to be progressive even with adequate glucose management. The underlying beta cell failure continues while the drug manages the symptomatic glucose elevation. 4-hydroxyisoleucine does something that most glucose-lowering compounds do not. It appears to have a protective effect on beta cell function, not just an acute insulin-stimulating effect. Animal studies have demonstrated that 4-hydroxyisoleucine reduces oxidative stress within pancreatic beta cells, preserves their mitochondrial function, and reduces apoptosis, the cell death that progressively depletes the beta cell population in type 2 diabetes. The seed is not just managing the symptom of insufficient insulin. In the animal data and in early human mechanistic studies, it appears to be protecting the cells that produce the insufficient insulin from the damage that was going to reduce their number further. No clinical drug for type 2 diabetes currently approved combines glucose-lowering action with beta cell protection in a single compound. Several drugs in development are attempting to achieve this. Fenugreek appears to achieve it through the combined action of 4-hydroxyisoleucine and the anti-inflammatory effects of its saponin fraction, which reduce the inflammatory cytokine environment in the pancreatic islets that is one of the primary drivers of progressive beta cell loss. The third mechanism is trigonelline and its effect on the enzyme dipeptidyl peptidase 4, more commonly known as DPP4. DPP4 is the enzyme that degrades GLP-1, glucagon-like peptide 1, the gut hormone that drives glucose-dependent insulin secretion, slows gastric emptying, and signals satiety. The pharmaceutical class of DPP4 inhibitors, sitagliptin, saxagliptin, alogliptin, work by blocking this enzyme, allowing GLP-1 to remain active longer after meals. Trigonelline, an alkaloid found in fenugreek seeds as well as in coffee, has demonstrated DPP4 inhibitory activity in vitro studies and in animal models of diabetes. The mechanism is compatible with, and potentially additive to, the GLP-1 pathway activation that metformin produces through a different mechanism. In a gut where fenugreek's galactomannan is slowing gastric emptying and its 4-hydroxyisoleucine is enhancing glucose-dependent insulin secretion and its trigonelline is inhibiting DPP4 degradation of GLP-1, the postprandial glycemic control is being addressed at 3 separate points in the same physiological cascade simultaneously. This is the compounding that makes the whole greater than the sum of its mechanisms. A drug typically has one primary mechanism, sometimes a secondary one. Fenugreek has at least 5 well-characterized glucose-relevant mechanisms acting through different pathways. The clinical result, the A1C reduction seen in the trials, is the aggregate of all 5 running simultaneously in a single teaspoon of seeds. Let me be specific about the clinical trial evidence because vague gestures at research shows are not good enough for a claim of this magnitude. A 2009 meta-analysis in nutrition research pooled data from 10 randomized controlled trials examining fenugreek supplementation in people with type 2 diabetes. The average reduction in fasting blood glucose across the pooled studies was 23 milligrams per deciliter. The average reduction in HbA1c was 1.3 percentage points. For context, metformin at standard doses produces A1C reductions of approximately 1.0 to 1.5 percentage points in clinical trials. The fenugreek data across 10 independent trials produces reductions in the same range. A 2015 randomized, double-blind, placebo-controlled trial published in the International Journal of Medical Sciences compared fenugreek seed supplementation to placebo in 60 people with type 2 diabetes over 12 weeks. The fenugreek group showed a reduction in fasting glucose of 26.2 milligrams per deciliter, a reduction in postprandial glucose of 31.7 milligrams per deciliter, and a reduction in HbA1c of 1.4 percentage points compared to no significant change in the placebo group. These are numbers that would make any pharmaceutical company proud of a drug trial. A 2016 trial specifically in pre-diabetic individuals, the population most relevant for prevention rather than management, found that 10 grams of fenugreek seed powder daily for 3 years reduced the rate of progression to type 2 diabetes by 4.2 times compared to lifestyle intervention alone. 4.2 times. The pre-diabetic individuals in the fenugreek group were more than 4 times less likely to develop type 2 diabetes over 3 years than those managing with lifestyle changes alone. These trials are not conducted by fenugreek supplement companies. They are conducted by academic medical institutions in India, Egypt, Pakistan, the United Kingdom, and the United States, published in peer-reviewed endocrinology and nutrition journals and reproducible across populations. Now, preparation matters dramatically. This is the detail that determines whether fenugreek does what the research demonstrates it can do, or whether it sits in a cabinet and does very little. The traditional preparation that has been used across South Asian, North African, and Middle Eastern medical traditions for centuries, and the preparation that most closely corresponds to the mechanism of maximum galactomannan hydration and 4-hydroxyisoleucine bioavailability, is overnight soaking. 1 tablespoon of whole fenugreek seeds, placed in a small glass of water at room temperature, left to soak overnight for 8 to 12 hours. In the morning, the seeds are consumed along with the soaking water before breakfast on an empty stomach. The soaking is not incidental to the efficacy. The galactomannan in the fenugreek seed requires water to fully hydrate into its viscous gel form. Seeds consumed dry, or seeds consumed as a powder without adequate hydration, do not achieve the same gel formation in the digestive system. The gel that forms during overnight soaking is partially preformed by the time the seeds are consumed, giving it a significant mechanical advantage in the stomach before gastric acid has the opportunity to partially degrade the fiber structure. The soaking water contains significant concentrations of 4-hydroxyisoleucine and trigonelline that have leached from the seed surface. Discarding the soaking water, which some preparation instructions suggest for palatability since fenugreek is bitter, discards a meaningful fraction of the active compounds. Drink the water. The bitterness is the medicine. Consuming the soaked seeds before breakfast is not a preference. It is a timing decision backed by the pharmacokinetics. Fenugreek's galactomannan needs to be in the stomach before the meal. It is going to slow the absorption of. Consumed with or after breakfast, it can still slow absorption of subsequent meals, but its effect on the breakfast glucose spike, typically the most pronounced of the day in diabetic individuals because of the dawn phenomenon, the cortisol-driven glucose release that elevates fasting glucose in the early morning, is significantly reduced. 1 tablespoon, soaked overnight, consumed with the soaking water, before breakfast. Every morning. This is the protocol. It has 2,000 years of empirical validation and 30 years of mechanistic and clinical trial validation behind it. It costs less than $2 per month at any South Asian or Middle Eastern grocery store. There are several things that fenugreek does not do that need to be said clearly. It does not replace insulin in people who require insulin. Type 1 diabetes and advanced type 2 diabetes with significant beta cell depletion require insulin therapy that no dietary intervention substitutes for. This is not the relevant context for fenugreek. It does not produce hypoglycemia in the way that sulfonylurea drugs and insulin can. The glucose-dependent nature of its insulin-stimulating action, specifically the glucose-dependent mechanism of 4-hydroxyisoleucine, means it enhances insulin secretion when glucose is present, not indiscriminately. This is a significant practical safety advantage, but it also means that people who are already on sulfonylureas or insulin and who add fenugreek should monitor their glucose and discuss dose adjustments with their physician, because the combined glucose-lowering effect may be additive. It does not produce the gastrointestinal side effects of metformin, the nausea, diarrhea, and abdominal cramping that cause approximately 20 to 30% of people on metformin to reduce or discontinue their dose at the doses established in clinical trials. Some people experience mild gas and bloating when introducing fenugreek, particularly at doses above 15 grams daily, due to the fermentation of galactomannan by colonic bacteria. This typically resolves within 1 to 2 weeks as the gut microbiome adjusts and is significantly mitigated by building the dose gradually rather than starting at the maximum immediately. Start with 1 teaspoon. Soak overnight. After 2 weeks, move to 1 tablespoon. The therapeutic dose in most trials is 10 to 15 grams per day, approximately 1 to 1.5 tablespoons of whole seeds. This is the target. The gradual approach gets you there without the digestive adjustment that puts people off in the first week. There are 2 foods that amplify fenugreek's glucose-lowering effect through complementary mechanisms and that are worth knowing about. Apple cider vinegar, 1 to 2 tablespoons diluted in a glass of water, consumed before the main meal of the day, produces its own independent reduction in postprandial glucose through acetic acid's inhibition of amylase and sucrase, the enzymes that break complex carbohydrates and sucrose into glucose for absorption. The mechanism is entirely different from fenugreek's mechanisms. Combined with fenugreek's galactomannan-slowing gastric emptying, the 2 interventions hit different points in the same carbohydrate-to-glucose conversion cascade. Trials combining them have not been conducted at scale, but the mechanistic logic for additivity is sound and the individual evidence for each is well established. Cinnamon, specifically Ceylon cinnamon, not the more common cassia cinnamon, which contains higher levels of coumarin and carries liver-related concerns at high doses, contains compounds called type A polyphenols that have demonstrated insulin-sensitizing effects through a mechanism involving the insulin receptor substrate 1 pathway, which is distinct from AMPK activation and from GLP-1 enhancement. Half a teaspoon of Ceylon cinnamon added to the morning soaking water of the fenugreek, or to breakfast, provides an additional glucose regulatory layer through this 3rd independent mechanism. None of these are dramatic. None of them require a significant reconfiguration of how you live. They require a tablespoon of seeds in water on the counter the night before. They require a bottle of apple cider vinegar and a jar of Ceylon cinnamon in the cupboard. The total cost of all 3 interventions combined is approximately $5 per month. What they represent at the molecular level is a convergent intervention at 4 separate points in the pathway from dietary carbohydrate to elevated blood glucose, slowed gastric emptying from galactomannan, reduced carbohydrate enzyme activity from acetic acid, enhanced glucose-dependent insulin secretion from 4-hydroxyisoleucine, and improved insulin receptor sensitivity from cinnamon polyphenols. 4 mechanisms, 3 foods, all running simultaneously after a single structured morning routine. Priya's endocrinologist, at her 6-month appointment, reduced her metformin from 1,000 milligrams daily to 500. Her A1C at that point was 6.1. He told her to continue whatever she was doing. She told him she was continuing both the medication and the seeds. He nodded. He said the combination appeared to be working. He did not ask her to stop either one. She is now, 20 months after her diagnosis, maintaining an A1C of 5.9 without any increase in medication. Her fasting glucose averages 104. Her continuous glucose monitor shows postprandial peaks that rarely exceed 140. She still takes her 500 milligrams of metformin. She still soaks her tablespoon of fenugreek seeds every night. She drinks the bitter water in the morning before breakfast because she understood from the mechanism why the bitterness was not incidental. Her daughter, who is 28, has started soaking the seeds. Not because she has any glucose problem, because she watched what the seeds did and decided she did not want to wait for the diagnosis before asking the question. There is something worth saying about how a seed that was used medicinally in ancient Egypt, in Ayurvedic medicine for millennia, in medieval European herbalism, in traditional East African and South Asian cooking as both food and pharmacy, arrived at 2024 with a body of clinical evidence that makes it comparable in effect size to the most prescribed diabetes drug in the world, and still sits in the spice aisle, unlabeled for its metabolic properties, purchased by people who are either cooking with it for flavor or following a family tradition without knowing the mechanism behind the tradition. It is not that the evidence arrived late. The evidence has been arriving for 30 years. What arrived late was the institutional interest in a compound that cannot be patented, cannot be manufactured exclusively, and costs $2 a month. The economic structure of pharmaceutical development does not naturally generate clinical trials for interventions that cannot produce a proprietary product. The trials that do exist were conducted largely in academic medical institutions in countries where fenugreek is a cultural staple, and researchers found the mechanism too compelling to ignore. The mechanism was always there. The seeds were always there. The gap was between the spice aisle and the endocrinology office. Between the kitchen of Priya's mother and the appointment where a prescription was written for a drug that discovered its primary mechanism by following the biology that the seed had been exploiting for 2,000 years. That gap is closing. Slowly in academic literature, faster in conversations like this one. The seeds are in the spice aisle. They are in every South Asian, Middle Eastern, and North African grocery store. They are available online for a trivial sum. A tablespoon in a glass of water. Left overnight. Consumed in the morning with the water they soaked in. The research is specific. The mechanism is worked out. The clinical evidence is 30 years old and still generating new trials because the effect is reproducible enough to keep attracting scientific attention. The prescription that was written without a conversation about the seeds is not wrong. The seeds that existed before the prescription are not a replacement? Both of these things are true simultaneously, and the space between them, the space where a soaked tablespoon of fenugreek seeds sits on a counter overnight, is the space that this conversation is trying to fill.